Hello everyone. For today's video lecture, we're going to be talking about the Impulse Momentum Theorem. The Impulse Momentum Theorem states that the net impulse exerted on a body over some period of time will be equal to the change in that body's momentum. In equation form, it looks like this. So J, which is our impulse, is equal to final momentum minus initial momentum. We had talked in the previous section about what impulse was and what momentum was. Here we're going to be applying this equation to solve problems. So to use the impulse momentum equation to solve problems, it's best to start by creating a diagram that shows the initial and final states of the body in question. So if possible, you want to show initial and final velocities that can include both magnitudes and directions, the mass or masses of the bodies in the system, forces, including magnitude and direction if those are known, and the times the forces are exerted. So momentum is mass times velocity, impulse is force times time. Each of those pieces are going to go into the diagram. So below is an example of a diagram I might use for a problem. So I might have some initial mass, or some mass, it's got some initial velocity and the angle with that. I have an impact force, I don't necessarily know the time. And then the final velocity might be my unknown in this setup. So if possible, you want to start with these diagrams. It always helps to put everything together and get it ready for the next step, which is the equations. So after the diagram is set up, the next step is to put values into your equation. Add any known forces, times, masses, and velocities. Determine what your unknown values are. And if the problem is in 2 or more dimensions, you're going to need to break that impulse momentum vector equation into components. So remember, these are all vectors, so we can have a impulse momentum equation for the x direction, for the y direction, and if we have 3D, we could have a z direction there as well. All right, so finally, last step is to solve your equations for any unknowns. With a one-dimensional problem, you'll be able to solve for one unknown. Two-dimensional problem, you'll be able to solve for 2 unknowns, because we split it into components. And 3 dimensions, we could do 3 unknowns. So the equations in these impulse momentum problems usually are not too complicated, but if necessary, you can always go for your equation solvers. At this point, the last step is just algebra. You're solving for the unknown values. So one additional piece that I want to throw in here is the idea of what's called the conservation of momentum. So we can see that in instances where there's no external force, and thus no external impulse on the body, the momentum would remain unchanged. So if J is 0, mv final minus mv initial would be 0, or the total momentum final would be equal to the total momentum initial. So this is known as conservation of momentum. And for a particle, this is rather uninteresting. So if there's no external forces, a body just kind of remains on its same course. It just kind of continues along its path. So that's more or less what the Newton's first law states already. But for systems of bodies, this can be a little more useful. So let's talk about that second instance. So for example, imagine a rocket traveling through space at a given speed. So we've got our rocket down here. It's got some mass, some velocity, some initial momentum. So at some point, explosive bolts separate and push apart the command module from the main engine. So got some boom, and then suddenly we split into the main engine part and the command module part. So if we define our system as the whole rocket, this is an internal force. It's because the explosive bolts are going to push equal and opposite on either side of this, and that does not create an impulse. So following through with our impulse momentum relationship, we can say that the total momentum of our system will not change. So our mass times velocity initial would be equal to the sum of mass A, velocity A, final, plus mass B, velocity B, final. So collectively, if I set this up and kind of solve just like I would for the other impulse momentum equations, this is going to be another alternative with a system of bodies. All right, so that's all we have for today's video lecture. Thank you for watching, and I hope to see you again.